So as I mentioned in class, we are only going to cover two laws in this particular section of the year. We have the combined gas law and the ideal gas law. Now we already covered the ideal gas law, so I'm going to work on combined gas law. Now there are a whole bunch of individual laws. They're called Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. You can learn all of those, and they're in the PowerPoint and they are online. But if you focus yourself in on this one particular formula, it actually applies to everything, and I'm going to show you how to make it work for all of the different situations you're going to face except for where you have moles. So in the ideal gas law, P, V, N, and T were always the same. They were constant. They never changed throughout the course of the problem. But what if you're in a situation where you go from a hot situation to a cold, or a high pressure to a low pressure? Well, if you have changing conditions, you've got to use a different formula because the PV equals nRT doesn't work for changing conditions. So we're going to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2. The only thing that's going to be held constant in this particular formula is our moles. So understand that amount of gas is equal to moles. So our moles are being held constant, our N. So like I said, have this formula, and we're going to use this formula in each of the next 4 examples. Make sure you watch at least the first 2 examples, and then if you understand it by the time I do the second example, don't watch the third and fourth. Or if you want to, pause the video, work the problem out on your own, and then fast forward until you get to the end. So here's example number 1. You have a sample of gas in a flask with a volume of 350 milliliters. At 25 degrees Celsius, the pressure of the gas is 135 millimeters of mercury. If you decrease the temperature to 0 degrees Celsius and the volume to 275, what is the gas pressure at the lower conditions? So just like I did before, when I did the ideal gas law, I'm going to list off everything I know. So I know that I'm going to be working with P, V, and T, and I'm going to be working with them twice. I'm going to fill in everything I know. So it actually doesn't matter which one you label as 1s and 2s as long as you're consistent, meaning you keep all the original volume, temperature, and pressures that go together as the same number. So they says I have a flask with a volume of 350 milliliters. That goes in under V1. That's what I'm deciding is going to be V1. It's at 25.5 degrees Celsius. Now remember, I always have to add 273 to all my numbers to get me to kelvins. So that's going to give me 298.5 Kelvin. And it says the pressure of the gas is 135 millimeters of mercury. Now, millimeters of mercury is just a unit of pressure. You don't have to convert it to atmospheres here unless they ask you to. So if you decrease the temperature to 0 degrees Celsius, so my new temperature is going to be 0.0 plus 273, which will give me 273. And the volume to 275, what is the gas pressure at the lower conditions? So I'm going to solve for P2. So now I'm going to plug in what I know into my formula. 135 times 350 divided by 298.5 is equal to P2 times 275 divided by 273. Okay, and I go to my handy dandy calculator, and I'm going to slide this over here and turn it on, of course. On. There we go. And I'm just going to plug it in. Now, I'm going to cross multiply. So I'm going to solve, I'm going to solve this way in my calculation. So let's see. So I'm going to plug it in the same way it's shown. So I've got 135 times 350 times 273 equals divided by parentheses, and I'm going to multiply. I'm going to divide it by what's attached to the exponent. Not my exponent, my variable P2. So which is 275 times 298.5, and I hit equals, and my answer is 157. So my pressure is 157. Now, I have to decide on the units here. The units are going to go back to whatever P1 was unless they tell me otherwise. So my units in this case are millimeters of mercury. So I'm going to write millimeters, Hg. Okay, so not that bad. Mostly a plug and chug. Now let's look at a slightly different example. So we have argon in a metal canister, and the pressure is 1 atmosphere and a temperature of 20 degrees Celsius. Over the next hour, the temperature is raised to 50 degrees Celsius. What will be the resulting pressure? So notice in this problem, we have a P1. We have our set of conditions. Now you'll notice that they gave me pressure at 1 atmosphere. So I fill that in. They gave me a temperature of 20 degrees Celsius. I'm going to add 273 to it to get 293. And it says over the next hour, don't care about time, the temperature is raised to 50 degrees Celsius. So my new temperature is 50 degrees Celsius. Plus 273 is 323. And it says what will be the resulting pressure. So I'm solving for pressure again. But they didn't give me a volume. What does that mean? Well, it's in a metal canister. Well, what do metal canisters not do when they're heated? They don't expand. They don't change. It's metal. It's going to stay the same. So if V is going to be constant, I can cross it out. And I just ignore it. So when I plug it in, I plug in my 1 atmosphere on the top, but now I have no V1. I just leave it blank. I plug in my T1. My P2 is what I'm solving for. I don't have a V2, so I'm going to leave it blank. So notice that I just left out anything that stayed constant. And I'm left with this formula. So I do it the same thing I did before. I'm going to cross multiply. 323 times 1 divided by 293. And I get 1.10. And again, it's going to be whatever the units of what I was given. I was given ATMs, so my answer will be in ATMs. Example number 3. A sample of CO2 gas has a pressure of 5.65 atmospheres and 125 milliliters. The sample is transferred to a new flask where it has a pressure of 6.99 atmospheres at the same temperature. That's going to be important. Let's remember this statement right here. What is the volume of the new flask? So I plug it in. Again, I list off what I know. So it tells me my pressure is 5.65. My volume is 125 milliliters. It tells me that the pressure is going to go up to 6.99. And it's going to be at the same temperature, which means temperature doesn't change. If temperature doesn't change, we're just going to cross it out. And it says, what is the new volume? So that's what I'm solving for. So again, I'm going to go back to the combined gas law and plug in what I know. My P1 is 5.65. My V1 is 125 milliliters. My T1 is constant, so I leave it out. Equals 6.99 times V2. My T2 is constant, so I leave it out, and I solve. So now this is just algebra. I multiply what's on the left, I divide by what's on the right. 5.65 times 125, enter, divided by 6.99 equals 101, which gives us a volume of 101 milliliters. Again, how did I know it was milliliters? I just have to look here. All right. Last example. When 5 liters of carbon monoxide at a temperature of 50 degrees Celsius is transferred to a 2.5 liter flask, the temperature decreases. What is the temperature at the new volume? Okay, so fill in what we know. P1, V1, T1, P2, V2, T2. So, it tells me my volume is 5.0 liters, and it tells me my temperature is 50 degrees Celsius. And again, it's going to be 50 plus 273, which is 323. Our P2, I'm sorry, the new volume is 2.50 liters. I'm sorry, 2.5 liters. And it says, what is the new temperature? So my new temperature is what I'm solving for. Now notice they didn't give me a pressure. Well, since they didn't give me a pressure, cross it out. Now we go back to our formula. So they didn't give me a P1, so I leave it out. 5.0 divided by T1, which is 323, is equal to P2, crossed it out, V2 times V2, 2.5, over T2, because that's what we're solving for. Again, we're going to cross multiply and solve for T2. So we've got 323 times 2.5, enter, divided by 5, equals 161.5. So 161.5 kelvins. Because remember, our units are kelvins. Now, it doesn't say Celsius. It doesn't say to put what's the temperature in Celsius. So I could leave it as 161.5 if I wanted to. But I don't have to. I'm sorry. If the question asks for Celsius, then obviously I would need to convert. But why do a step when you don't need to do a step? Because it's an easy way to make mistakes. So let's just leave it as 161.5 and be done with it. So as you can see, I gave you 4 very different situations. One involving volume and temperature, one involving all 3, one involving pressure and volume, and one involving pressure and temperature. They all can use the same formula. Just cross out what you don't need, leave it out of the whole thing, and you're good to go.